This is Beyond Replication, a holistic approach to application scaling. Thank you for joining. My name is Josh Thornton. I'm a founding engineer at SpeedScale. I wrote and maintain the world's most realistic load generator and mock server. At SpeedScale, we kind of work with network traffic that we capture and then use that for load generators and mock servers. So part of my job is interacting with customers and helping them scale up their applications. And regularly as part of my job, I'm evaluating both our internal applications as we grow, so we're a startup, and the customers who use our tools to scale their own applications. So in this talk, you'll learn how to approach a problem of scaling your application, when you should look at things like that, tools for diagnosing issues, pitfalls to avoid. We're going to look at a few Go p-profs, and we'll go deep on some things, but we're really going to skim the surface of this area because we don't have 12 hours here, and performance tuning is kind of a big topic. So when I talk about application scaling, usually we're talking about response time, so the amount of time between when a customer requests something from your application, when they get an answer, and the total throughput, so how many of those customers doing the same thing you can handle at the same time. And usually in the talk, when I say application, I mean like a single process that you're running, and I'll use the word system to talk about your entire set of services that make up the external service that customers interact with. So really, why do we care about this? If your application is not performant or doesn't scale well, your customers are going to get errors or slow response times. If your app is public, you'll be dropped down on SEO, and you won't be bringing people in as much. So realistically, the answer is money. And if you can provide a better experience to your customers, then you are more valuable to your organization, and they will pay you more. That's also about money. There's also something, if you've been on Hacker News, you may have heard of the hug of death. So this is where on Hacker News, you have a post about your company, it rises to the top, and potentially tens of thousands of people are trying to access your service and your site and sign up, and that's really the time when you need to scale. Those people, if it doesn't work the first time, they're not coming back, right? So you need to be ready. So where do I start is a question that we want to address here. There's so many ways to address scaling, a million things to look at, and a million ways to approach it. At a high level, you want to be ready before you need to be ready. Okay, so load tends to come unannounced, like we said with the Hacker News hug of death. You need monitoring in place so you know what happens. You don't want your customer to tell you that your application isn't scaling or that they have errors. You want to be able to see what's going on, and you really want an internal view. You want runbooks. If you're having a problem with your application and you need to go to the next level, that's already a hard enough problem, so make the easy things easy. Scaling your apps, resizing volumes, have runbooks to make sure you can move through these quickly. Understanding scalable patterns would be application patterns, architectural patterns for doing these. There's a ton of good books for that. And really load testing ahead of time, and load testing ideally, or detecting load regressions in CI and CD before you deploy is critical, because these things rarely show up in dev, right? Like if you have a performance issue, you're not going to notice on the app running on your laptop. You're going to notice when you have 1,000 people looking at it. So the part of the talk is beyond replication. So replication is more servers, or just bigger servers, bigger nodes. So this generally doesn't work because your code may be inefficient, which may scale properly, but will cost a lot more money long term. A slow third party, so if your app scales properly, but a downstream service, either that your company owns and runs, or something that you're talking to doesn't scale, can be an issue. Of course, there's architectural constraints. Maybe you really need a time series database and you're using something transactional. It doesn't really fit your model. That's going to slow you down. But the biggest thing overall are synchronization bottlenecks. So this is coordination either within an application, within a process, or across processes. This is what I see a lot. So databases have even dropped down to table and row level locks, but if you're accessing the same thing, or if you're accessing a shared key and a cache that's being rewritten and read, it's going to slow things down. Or heaven forbid, a centralized coordination among processes. So this is really the graph that you want for scaling your app. This is what a blog looks like. Okay, so medium.com has, they have bigger stuff, CDNs and caches, but they add more nodes. You're serving static assets, and so you get a higher throughput from adding those resources. Unfortunately, most applications don't work this way, right? You've got some sort of coordination in the middle that's going to slow things down, and just adding nodes, while it may get you a little higher, is not really going to get you there. Also, this little dip at the end on my highly detailed graph here shows what generally happens when you start really utilizing your resources. Things tend to get shaky because at full utilization, everything gets unpredictable. You'll see big bursts of throughput and then big drops. So we've got a cycle here that can tell us how to analyze and try and deal with these things. So first we evaluate, is it good enough now, right? We measure because we want data-driven decision making. We never want to guess about these things. We want to analyze, taking all the data that we have and actually figuring out what's going on, which is usually the hardest problem. This is why humans are involved, and LLM isn't going to solve this part of the problem for you. And then we have to implement and change the system in an effective way. And importantly, once it's fast enough, stop. If you've never optimized an application or a system before, you'll get a big boost up front, and then you will spend forever trying to eke out the little changes near the end. And only you know when it's fast enough. So your system is a unique butterfly. Now, some parts of your system realistically will have known solutions. If my database is running slow and I need to add an index, then for MySQL or Postgres, you can look at that and there's a known solution to that problem. But your system as a whole is a combination of all different kinds of implementation decisions, and only you can really tell when your system is good enough, when it's fast enough. So you have a 5-second response time. Is that too much? If you're an e-commerce website, then yeah, that's a lot, that's too much. Are you generating a report for 3 months of data? 5 seconds is probably fine, right? It's important to consider your access patterns and your customers, and always measure your results at the customer level, what the customer is seeing, right? Not some little interaction between your process that got a little faster, but what does the customer actually see? So if we're looking at the measure part of the cycle, we want to care about metrics like throughput rate, so how many services or how many requests are going through my system at one time. Errors, very important to consider errors because errors are often the fastest. Okay, so if your application is making a database request and it gets all the way through and does some database processing, that's a lot slower than the database isn't ready and I get a 500. So you start spitting errors, it's going to look like your throughput went way up, but it's not what you want to see. Latency duration is how long these requests are going to take, measuring that as a whole, but also for particular operations. And then saturation for things that you can measure. This is 100% of what my system can handle. How close to that am I? Which is going to change how you look at things. And you can reference the read and use methods are good systems to look at this. When you're looking at these, anomalies are very important. So if you're looking at a graph of throughput or latency and you see a big spike or a big drop, those things may be really short in time, but can often indicate a deeper problem, and it can often tell you where to look. So don't just write those off. And then it's super important to care about tail latency. So the P99 is the requests that are slower than 99% of the other ones, and the P999 is the 99.9 percentile slowest requests. And these are often a very small fraction of the requests you have, but they're usually the most important, because who is utilizing your system the most? Who has the most data and the biggest database tables? Those are the customers that are paying you the most. Those are the ones that you want to care about the most. So tools to use are simple metrics. These are great because they're easy to implement and understand. They're tailored to your specific need. You know, when you put in a very specific metric, there's no wondering about what that tells you. You know exactly what it is. And not just for overall latency, but you can even, you know, track very specific things within your application. These will definitely come in handy later when you need them. There's also built-in metrics. So these are for RDS. Many of the tools you use already export metrics, so they're there. You should use them. And usually in the observability space, you have metrics, logs, and traces. Logs won't help us as much in this case. Traces may. Traces will tell you essentially across your whole system. It'll help you narrow down into what's causing the issue. But the problem with traces often is that if you don't have tracing everywhere, it's a lot less valuable, right? If you have a chain of, you know, 5 services and one in the middle doesn't propagate your traces, then you're not going to get the information you need. And in larger companies with more services, this can be hard to get adoption. In the measuring tools, we have load testing tools. So SpeedScale makes a load testing tool. That's me. But also there's JMeter and there's Vegeta, and you can use K6. And there's actually like a ton of these, probably because it's easy to write a basic load generator. You know, you're just sending requests at your service. But the important part is to use realistic load. Okay, so look, I've written the load test for your service here. This is a K6 load test. We have 100 virtual users. We run 100,000 iterations, and we hit your health check endpoint and see if it returns a 200, right? So we're done. That's all we need to do. But the problem is you're not really testing the system, right? How many API endpoints, how many endpoints does your API have? How many permutations are there in total? Because one endpoint, like the get orders endpoint, may have some differing logic based on what the user is requesting. And getting a realistic sample when you're trying to test your application to make sure it can handle higher load is critically important. So we use Go at SpeedScale, and so I'm familiar with looking at pprofs. There's also, you know, other profiling tools for other languages. There's Visual VM for Java. There's several profilers for Rust. Intel vTune is good if you want to look at very specific information about your CPU and see how it's you know, handling cache data. And if we look at this profile here, this is from an error that we discovered where we had a large loop that was adding fields to a logger recursively in the loop, right? So every time we ran the loop, it would add the same fields to the logger over and over, and the program crashed because 85% of the memory was being used for log fields, right? Here's another one. This one's actually a lot more obvious, points to one place where everything is going through a single mutex. Down there at the bottom, that's our biggest block. and 83% of the mutex time is going through this single mutex. So these pprofs will really help you narrow down when you're looking at performance within a particular process or application. This is the Go execution tracer, another Go specific tool, but can give you really detailed information. The execution tracer has a high learning curve, but can give you really detailed information. So in this case, all the little lines in the middle is small tasks being shifted between Go routines. And we could see, you know, things are generally going along well. And these two big blocks on the side is where nothing at all is happening. And it's waiting for this net.sysdialer.dial. And what's happening in this case is we're waiting for network connections. So this was an improper reuse of network connections in an application that uses them a lot. And we would create tens of thousands of sockets in use. Those were being closed but sit open in a time wait state, which hangs around waiting for delayed packets to come in when one side of the connection is closed. Ran out of file descriptors, and so we have the application just sitting here waiting to dial on all CPUs. Grafana is here at the conference, and they maintain this tool called Pyroscope, which is pretty good. Pyroscope is multi-language, also does continuous profiling, and gives you a diff between profiles, so that's pretty handy. And newer versions, I'm told, will give you an AI text-based description of your profile if you're into that sort of thing. BPF trace, there's been a couple of talks on this. You can go really deep into kernel level visibility. This is super powerful. It's probably not what you need. This stuff is really interesting to go down and look at, you know, optimizing the TCP stack, but realistically, unless you're at you know, a FANG company, you haven't already optimized your system in bigger ways, and there are ways to, you know, reduce the amount of work you're doing by 10x. It's important to measure before you need it. Like I said, you'll almost never find these issues on your laptop or in dev. You'll find them in prod. So you can do the continuous profiling like we saw with Pyroscope. We have a way to do on-demand profiling, so I can send a signal and create a profile if something is not looking right, and generate that. And you can also do this in CI/CD. So validating performance requirements alongside other tests is something that more mature organizations will do because they're the ones that have hit these problems before. They've released things and either introduced a regression to where now you are at a certain performance level, you're higher, and your current infrastructure cannot handle it, or you just get a bunch more users and you need to make sure that you're able to handle that sort of load. Then we move on to the analysis phase, where we want to identify the bottleneck and take all the data and information that we've collected and use it to determine what our problem is. This is often the hardest part of the process. Sometimes your app is just doing a lot. Again, usually not. If you haven't really dug into this stuff before, there's often a lot of things that you can optimize, but it's difficult because it can require looking at everything depending on the scope of the problem and where you find it. The scope of the problem may be your entire system, and that could be really hard to narrow down. So again, having those measurements ahead of time will help you get there. So just like any issue that you're dealing with, problem that you're trying to solve, really understanding the problem is core, being able to recreate it locally, and only targeting the spot where the issue is really occurring. You can spend a ton of time optimizing things that look inefficient that won't actually make your app faster. I've done a bunch of that, and but it's not going to get you there. So really making sure you understand these tools is important. which brings me to the next point, which is looking at this before you need to. If the first time you look at these performance metrics is when you're having a problem, or heaven forbid, the first time you try to create them when you're having a problem, you're not really going to be prepared. If the first time you look at a profiling tool is the first time when you're having an issue, then you're not going to know what bad looks like. So you can't, you can't fix the problem because you don't know what it looks like when it's good, right? The first time you open the hood of your car is when something's broken. You're not going to know what to fix. It's also important to ask for help, talk to your communities. This is small text, but me asking someone in the Go community, in the performance channel, hey, look at this pprof and help me out. They say, it looks like there are a ton of timers in your app firing very often. And I said, wow, my app is creating a disturbing number of timers, not reusing them, and it was causing an issue. And this is the pprof of that. So we've got the runtime.run timer, runtime run one timer, and the sift down timer. The word timer's in there a lot, obviously in retrospect, but I didn't really know what I was looking for. These are all internal Go methods, not things in my code. So when you get to the implementation phase and you want to change the system, it's helpful with like any other problem to make the smallest change possible to validate your assumptions. Follow the scientific method. Don't be gentle. I think often we make a fix and then you say, hey, I've been running this one little test, this one little check to see if my fix worked, right? And once that passes, I'm done. But then you go and release it and somebody's going to use it in a different way. So try to break them and just avoid complexity everywhere you can. Complex systems are harder to understand, debug, change, and these problems can be hard enough already. You don't want to be dealing with spaghetti code or a spaghetti interaction between components when you're trying to analyze the performance of the system. And then you do it again, right? It's very unlikely you will solve this on the first round. I would say try and learn it every step and keep notes because the problem space can be large. There's a couple of generalized strategies for this. First, there's configuration. So these are, there's more and faster hardware. There's database indexes. Your runtime generally has ways to tune the garbage collector. Go has a Go max proc setting to avoid CPU contention. Java has a ton of flags for this sort of stuff. Your operating system has ulimits and network stack tuning, and if you're in Kubernetes or some other platform, there's a ton of stuff there. And those are the easiest to change. Those are the ones that you can flip a switch and get something out of it. Beyond that, there's in-application, which might be caching, avoiding sending data over the network. Predictive preloading is, I know my customer might need this. I'm going to spend a little time and effort. This would be reducing latency within your application. Retry with backoff. You don't want to run through a 15-step process inside your app or multiple apps and then die in the middle because one of your services was unavailable for a second. So there's also architectural patterns. Hopefully this is not what you need because these are the hardest to change, right? These are going to be potentially multi-week, month efforts with a lot of meetings in between. But getting closer to the client would be like a CDN or edge computing. The circuit breaker pattern will let you avoid going further if there are errors. So that will generally return a good response to some users and a bad response to other users faster rather than everybody waiting longer to get a bad response. Pull-based architectures can work well here because if I'm sending a ton of requests at a synchronous API and it has to respond right now or it dies, then under load it might die. So having servers that can pull from a queue and do the work as fast as possible will better utilize those resources. Reduced hops between services and stateless services make horizontal scaling a lot easier. And we talked a little bit about continuous performance testing earlier, right? So this is where I might have my application in CI or CD, and I say, I really want to do a performance test on my app before it gets released out to production so that I can detect these issues. And this is really easy. You have your app, and just like you would run a set of tests against your app, you just take a load balancer, or a load generator, excuse me, stick in front of your app, and send it a bunch of load. Although I did forget that now that you're sending load at your app, real network traffic, it's going to try and access information in the database. And this is in our shared environment here, but that's where all our data is. I don't really want that because somebody's going to delete my table or change things, and it's not going to be hard to replicate. So I'll just move that into my pipeline. But now I forgot I need data in there. But I can just add data, store some, I'll preload it with the data that I need. I also forgot that there are other APIs that I need to talk to, and those APIs have their own databases and APIs, and some of these may be external, which is outside of your control. So maybe this is not as easy as we thought, but there is a way that we can get here. So if we have our app and a load generator, we can back our app with mocks. So people feel differently towards mocks, especially in like a unit testing context, because a mock isn't necessarily the real thing. And when people write mocks, they make assumptions and they code their assumptions into the mocks. But for any sufficiently complex system, mocks are really the simplest way to create a reproducible environment. And the alternative to this is kind of like an ephemeral environment where it stands up all the other dependencies, but I wouldn't expect that to be cheap or easy to implement, and then you still have third parties that are outside of your control. I would recommend, if you're using mocks like this, there are several tools that can take real traffic and create mocks from it. That's my preferred method because you really do want something that's as close as possible to the real thing. And then once you've set up mocks, you can create a subsystem where you group a number of applications, a part of your system in there, and use the mock server, and then test performance through those, getting real verified requests in and out without a lot of the extra complexity. And that's it. Thank you. Yeah, anybody have questions I can answer? No? Thanks a lot.